Good morning. Today we are going to see about the formulation of economic load dispatch problem. The last class we have seen what is meant by economic load dispatch and what are the constraints. So what is meant by economic load dispatch? Economic load dispatch is defined as optimal allocation of generating units to the generating station with satisfies the demand and also with the minimum cost function. Okay, with satisfying the demand and also with the minimum cost function. So what is the main objective function? Objective function of economic load dispatch? The main objective function of economic load dispatch is to minimize the total fuel cost. Next, what are the constraints? Constraints are of two types. One is power balance constraints and another one is minimum and maximum operating limits. So what is power balance constraints? So whatever the generation that is happening, that equals the demand. So that is called your power balance constraints. What is the minimum and maximum operating limits? Minimum and maximum operating limits. So whatever the power that is being generated in the generating station, that should be within the minimum and maximum operating limits. So that is the definition of economic load dispatch. So sometimes in 2 marks, if they ask now, you have to write whole thing. Okay, if they simply ask define economic load dispatch, you have to write what is the definition and as well as the constraints. To the constraints, then with the formulation also that we'll discuss. So general formulation. So what is the general formulation? So what is the main objective function? The main objective function is to minimize the total fuel cost. Minimize the total fuel cost. That is minimizing the FT of P. Okay, FT, total fuel cost. Minimizing the total fuel cost, FT of P, is nothing but sigma, that is summation I is equal to 1 to N, Fi of PA. Okay, so where N is number of generating units, okay, participated or operated in that particular period of time or participated in that particular dispatch. Okay, so that is nothing but capital N. Then Fi of PA is the fuel cost function. Okay, fuel cost function. That is nothing but Fi of PA is equal to AI PI squared plus BI PI plus CI. Okay, so that is in rupees per hour. Rupees per hour. So if it is first generating units, F1 of P1 is equal to A1 P1 square plus B1 P1 plus C1. If it is 10th generating unit, up to 10th generating unit, F10 of P10 plus A10 P10 square plus B10 P10 plus C10 rupees per hour. Okay, so this is the fuel rate characteristics. Fuel rate characteristics. So this axis is power generated, output power generated. That is in megawatt. Output power generated is in megawatt. This axis is in fuel cost. Fuel cost, that is rupees per hour or dollar per hour. Okay, so whichever the country you want to settle in future, that okay, that rupees you can put over here. Okay, rupees, dollars, yen. Okay, like that. Whatever the country you want to settle over in the future, that okay, that rupees you can, that notation you can keep it here. But now we are in India, so we are following rupees. So rupees per hour. Okay, so with the increase in the fuel rate, automatically your power generated also will be go to the maximum. Will be the maximum, but it should be within the minimum and maximum operating limits. That is some minimum operating limit and as well as the maximum operating limit. Okay, so every optimization we have seen before, no, every optimization function has some objective function as well as the constraints. Okay, objective function as well as the constraints. Okay, as I said, like what is the student's objective function? You have to study for less period of time, or day before the day of exam, or daily half an hour or 1 hour, but you want to get very good marks. Okay, 100% out of 100%, you need to get above 97, 98% you need to get. Okay, but you need to study only for the less period of time. But what is your main objective? Students' objective to get more marks. What is the constraints? They need to study daily 1 hour or half an hour in a day. Okay, or day before the day of the examinations for 8 hours, 10 hours, like that they want to study. But what is their main objective? They need to get full marks. Okay, so that is the. So similarly, like what is the objective function of economic load dispatch? Minimize the total fuel cost, ft of p. Okay, f suffix t of p. That is nothing but summation I is equal to 1 to n fi of p. Okay, so what are the constraints? Two constraints we already discussed. So one is power balance constraints. So whatever the generation, that is generation here, PI is nothing but total, that is power generated from the ith generating unit, or P1 is nothing but power generated from the first generating unit, or P3 is nothing but power generated from the third generating unit. P8 is nothing but power generated from the eighth generating unit. Okay, so I, whatever the I you are choosing, that is this. So PI is nothing but power generated. Okay, total power generated from that particular generating unit. So what is first constraint? Power balance constraint. So generation that equals the demand. Generation that equals the demand. So we can write like this now. PI is equal to PD. Okay, generation, whatever the power generation. So PD is nothing but demand, power demand. Okay, P suffix D is nothing but power demand. So whereas PI is nothing but power generated at the ith generating unit, or P1 or whatever it may be. So summation I is equal to 1 to n, PI is equal to PD. Okay, so this is the power balance constraints. So what is the minimum and maximum operating limits or capacity limits, or power generation operating limits or power capacitor limits? So whatever the generation, that is PI is nothing but generation. Whatever the generation that is happening, that should be within the minimum and maximum operating limits. Okay, so this is what is the minimum operating limit. So we are taking as PI minimum. Okay, PI minimum less than or equal to PI less than or equal to PI maximum. Say for example, for a 1000 megawatt generator is there. So maximum power generation can happen up to 1000 megawatt. So PI maximum I am taking it as 1000 megawatt. So PI minimum I am taking it as 800 megawatt. So PI. So whatever the power, say for example, power generated from the first generating unit. So 800 megawatt less than or equal to P1 less than or equal to, here PI maximum is 1000 megawatt. Okay, so like that I will be choosing over here. So minimum and maximum operating limits. Okay, so up to this 2 months, you have to write what is the objective, first definition, what is the objective function, then what are the two constraints. So power balance constraint, that you have to write that definition, this equation, then minimum and maximum operating limits. So that also you have to write that what is that minimum and maximum operating limits. Then you have to write this limits. Okay, so up to this 2 months. So if you write only definition like that, then you will get 1 marks or half marks based on what you are writing. Okay, if you write this, so no need to see in the thing itself. Full 2 marks will be awarded for you. Okay, so this is your first 2 mark question. Next, so this we formulated. Okay, so next thing is that we have to find the solution. We have to find the solution for this. Actually, now we have objective function as well as the constraints. Objective function, we have to objective function and the constraints. So we have to find out the optimal dispatch, that is economic load dispatch. Okay, so this we have to find the solution. Okay, we have to find the solution. 1 minute. Yeah. So we have to find out the solution. Okay. There are n number of methods to find out the solution for economic load dispatch problem. There are many optimization methods are there, techniques are there, methods are there to find the solution for the economic load dispatch problem. You can't specify that this is the only particular technique so that you can solve the economic load dispatch. Like that, you can't able to tell. There are many methods, many optimization techniques is there. In the forthcoming classes, one class we'll see that thing. Okay, but there are many. So one such technique is Lagrange, by solving using the Lagrange's function method. Okay, Lagrange's function method. So what is Lagrange's function? So what is Lagrange's function is that this is the general formulation of Lagrange's function. So Lagrange's function is defined as objective function plus some constant into constraints. Lagrange's function is defined as objective function plus some constant into constraints. So here objective function, I already told, minimize the total fuel cost. Constant, I am taking it as lambda plus constraints, power balance constraint. Say for example, for economic load dispatch, what is the objective function? Minimizing the total fuel cost. Okay, minimizing the total fuel cost, F suffix T plus some constant. I'm taking das lambda plus constraints. Constraints is nothing but we formulated now PI is equal to PD. That is power balance constraint. Power balance constraints or PI minus PD is equal to 0. That also you can take. That formulation now we are going to see. So this is the Lagrange's function. Okay. So Lagrange's function is defined as objective function plus some constant into constraint. So here what is the objective function? Minimize the total fuel cost. That is FI of
Ravi kada
FI of PI.
మరి టికెట్ బుకింగ్ లో ఏదో కొత్తగా వచ్చింది.
FI of
టికెట్ పంపించారు ఒకటి
PI. Okay, plus some constant, that is lambda into what is the power balance constraints? That is nothing but whatever the power generated that equals the demand. That is PI is equal to PD. We have already seen. Okay, so here how I am taking it as PI minus PD. Like that I am taking. That is PI is equal to PD. That is nothing but PI minus PD. Summation I is equal to 1 to n PI minus PD. Okay, so generally if you see generally in the practical, but the general formulation is for whatever the power generation that equals the demand. But generally in the practical thing, demand is more than the generation. Okay, so say for example we are generating 1000 megawatt, but we can't say generally the load might be increasing only. Always it might be increasing only. Okay, so we can't predict the load. Okay, nobody we can predict approximately. Okay, approximately we can predict, but accurately no one can predict the load. Okay, so generally in practice, in real world, the demand is more than the generation. So what I'm doing is I'm rewriting this equation as PD minus PA. Okay, PD minus PA, because equal to sign only. So either you can take PD minus PA or PA minus PD, but generally demand is more. Demand is more because we don't know. In the meanwhile, what we'll do is we'll switch on some other loads immediately. It might be increasing only. If you take that load curve and load duration curve of the particular day. So generally it might be increasing only. Okay, so we are taking this demand PD minus sigma I is equal to 1 to n PI. Okay, so up to this we have taken. Okay, so next what we are doing is we are differentiating the Lagrange's function as you did in say for example you I think already this say a similar type of problem you have solved in your mathematics 3. while solving linear equation. Okay, I think linear equation, non-linear equation. I think non-linear equation, what you're doing is we are considering the non-linear equation as linear one, and you're solving the problem. Some iron problem like that, and all you solved in mathematics, no? In mathematics 3, in discrete mathematics, I think so. So I think already you solved. So now we want to find out the change in the fuel cost, change in the fuel cost. Okay, we want to find out the change in the fuel cost. So what I'm doing is I'm differentiating. I need to find out the small change in the some change in the, because Lagrange's function we form. Next to what we have to do, some small change in the like a fuel cost I need to find. So what I'm doing is I'm differentiating this Lagrange's function and equating it to 0. Okay, suppose I'm differentiating and equating it to 0. So here why I'm differentiating it is that I need to find out the small changes whatever happened in that particular fuel cost changes, and I need to optimize my fuel cost. That is my main objective function, no? So I need to optimize, that is minimize my total fuel cost. So I need to find out what is the changes with respect to my demand and as well as the generation, that I need to find out. So what I am doing is, that's why I am differentiating and equating it to 0. So if I need to find out a very large changes, say for example, like that, say you need to go for the integrating. Okay, integrating that equation with some limits, say for example from 0 to t, or some time t, or 0 to 24 hours, like that also you can go for large change. So now I need to find out this some change in the fuel cost, small change in the fuel cost. So what I am doing is I am differentiating this term, I am differentiating and equating it to 0. Okay, differentiating and equating it to 0. So what I'm doing is I'm neglecting this demand. Okay, demand is large, I'm neglecting. Okay, generally the demand is increasing and demand is large, so I'm neglecting this demand. Now I'm differentiating and equating it to 0. Okay, so after differentiating, how it will come? Differentiating with respect to power generation, that is pi. Okay, so this is Lagrange's function, L of f. L of f is nothing but Lagrange's function. So now what I am doing is I am differentiating this Lagrange's function, okay, and equating it to 0. Differentiating the Lagrange's function and equating it to 0. So dl of f divided by dpa with respect to pi, with respect to the power generation, with respect to power generation. Okay, I am differentiating. So what here it will come, fi into of p divided by dpi plus here lambda is constant. Okay, this is neglected, minus pi. So if you're differentiating pi, it is 1. So it will come minus 1. That we are equating it to 0. I already told, no, equating it to 0. So after equating it to 0, so after that rewriting, we'll get dfi into dpi divided by of df of I divided by dpa. Okay, in short form you can take like df of I, sorry, dfi divided by dpi is equal to lambda. Okay, for what limits? That is for limits pi is should be within the pi minimum and as well as pi maximum. Okay, whatever the power generated, that should be within the pi minimum and as well as with the pi maximum. That is pi minimum less than or equal to pi less than or equal to pi maximum. Okay, so this is dfi divided by dpa. Okay, so in generalized term we can write like this: df1 of okay, df1 of p1 is equal to df2 of p2 is equal to, or df1 if you take like nth generating unit, df1 divided by dpn is equal to 0. Okay, is equal to 0. Okay, then this is the first condition. If dfi divided by dpi is equal to 0 now, the condition will be like this. That is dpi minimum is less than or equal to pi less than or equal to pi maximum. Suppose dfi, that is change in the fuel cost with respect to bar, is less than or equal to lambda, then pi is equal to pi maximum. If dfi divided by dpi is greater than or equal to lambda, yeah. If the function to be the minimum, what we generally do after this is the objective function minimizing the total fuel cost. So Lagrange's function is nothing but objective function plus some constant I'm taking it as lambda, then the constraints, that is pd minus pi. Okay, so I'm taking this demand outside, that is pd minus pi. Okay, so where demand is more, I'm just neglecting the demand. Okay, and what I'm doing is I'm differentiating and equating it to 0. While differentiating, you will get dfi divided by dpi is equal to lambda. Okay, for pi is less than or equal to pi minimum is less than or equal to pi maximum. That is whatever the power generated, that should be within the minimum and maximum operating limit. And as well as next step, then dfi divided by dpi is great. Okay, dfi divided by dpi is greater than or equal to, sorry, is less than or equal to lambda for pi is equal to pi maximum. Then dfi divided by dpi is greater than or equal to lambda for pi is equal to pi minimum. So these are the some important conditions that we attain. Okay, change in the fuel cost with respect to the power load dispatch of n thermal generating unit to serve the load. Okay, so if you see this figure, this is the economic load. This is the economic load dispatch of n thermal generating units committed to serve the load. Say, for example, now you take the n boilers are, okay, n boilers are there. Boiler 1, boiler 2, up to nth boiler. It might be 3, 4, 5, 6, 10, 100, 500, whatever you want to take in the n. Okay, so generally n thermal generating units we are dealing with. So n thermal generating unit. So 3 boilers is that, you know, from here we are giving the enormous amount of okay, heat to the boiler, so that from the boiler superheated steam will be generated. Okay, and it is directly given to the turbine. Okay, turbine is rotate. This turbine is coupled with the generator. Okay, this generator is connected to a common bus, and it is committed to serve the load P load. Okay, power generation that is connected to serve the that is connected to bus, and from the bus it is connected to serve the load that is called P load, P suffix load. Okay, so from the boiler, okay, this is the first boiler. The fuel supplied to the first boiler is F1. Okay, the fuel supplied to the first boiler or fuel cost function, whatever you can take, fuel cost function of the first boiler is F1, and the heat generated in the boiler 1 is H1. Already we have seen. Okay, H1 of P1 or H1, what all are same only. H1 or H1 of P1, F1 of P1. But generally fuel supplied to the first boiler is F1. Okay, so turbine that is connected with the first generating unit is T1, and generator of the first generating unit is G1. From the G1, so what, how much power is being generated? P1. So P1 might be of, for example, 1000 megawatt. Some P2 might be of 500 megawatt. P3 might be of some 2000 megawatt. Like that, it may vary. So similarly, the fuel supplied to the second thermal generating, all are thermal generating unit only. Okay, so that is n thermal generating unit. So that is this is the second thermal generating units. So boiler is second boiler, turbine T2, generator G2. So power generator is P2. It is connected to the common bus. Again Fn, nth generator. Fuel supplied to the nth boiler is Fn, boiler N, turbine T3, generator G3. That is power generated from the third generator is P3. That is connected with the bus, common bus, okay, and connected to serve the P load. So first you have to draw this diagram. Suppose the exam they may ask, describe about the N thermal generating units, economic load dispatch of N thermal generating units committed to serve the common load. Something like that. The question may be asked, some 10-mark question or 15 marks, 16 mark question, like that they may ask. So what you have to do is first you have to draw this, then you have to explain like that I have explained, no? So there are 3 generating units, the n generating units. So the boiler, first boiler, so heat is being given to the boiler H1. It is, you can also add here H1, okay, heat is given to the boiler as H1. Then T1, turbine T1, this story you have to write after drawing this diagram. You have to write that story, okay, whatever I told, that story you need to write. Okay, then you have to define the economic load dispatch, definition of the economic load dispatch. Then after that, the constraints. Then what is after that, the constraints? Then what is objective function? So the next we have to go to this point. What is objective function? So what is the after writing the definition, then the constraints, then what are the types of constraints? Power balance constraint, minimum maximum operating limits, definition, and as well as that limits everything, equations. Then you have to come like what is objective function? Objective, what is the main objective function? Is to minimize the total fuel cost. Is to minimize the total fuel cost. That is nothing but sigma I is equal to 1 to n Fi of Pa. Okay, sorry, summation or sigma summation is the correct. Okay, summation I is equal to 1 to n Fi of Pa. Okay, then this is heat rate characteristics and fuel rate characteristics, all are same. So here you can write two units, that is rupees per hour, and as well as heat H in the bracket you have to mention like MTBU, okay, MBTU, okay, million British thermal units per hour. So that also heat rate and fuel rate are in the same axis. It is directly proportional to. So you can write here, like yesterday we have seen, no, that same, like that we have seen. Yeah, here we have seen heat rate. Yeah, this curve we have to draw. That is H of MBTU per hour. Okay, that is the heat rate. Then fuel cost is nothing but rupees per hour. Okay, this is this axis. In this axis, output power generation, that is in megawatt. Okay, so linear curve we have to draw the linear curve, that is with respect to like a change in the heat or change in the fuel cost. Automatically the power generation also, it is linearly increasing to the maximum. Okay, so this is the minimum power that is being generated, maximum power that is being generated. So this curve you have to draw, and you have to explain about this curve. That stories you have to explain how the curve is linear, everything that you need to explain. Next, you have to come, yeah. So the constraints. Okay, so we have formulated the objective function subject to constraints, subject to power balance constraint. So what is power balance constraint? You have to define here. So whatever the power generation, that is equals the demand. So that is nothing but so this also you have to write Fi of Pi is nothing but AI Pi squared plus Bi plus Pi plus Ca, rupees per hour. So power balance constraints. What is power balance constraint? Whatever the generation that is happening, that is equals the power demand. That is nothing but summation I is equal to 1 to n, pi is equal to pd. Okay, so next is this limits. That is whatever the generation that is happening, that should be within the minimum and maximum operating limits, or otherwise like lower and upper operating limits. That also correct. Okay, instead of minimum, you can also write upper. Sorry, lower, upper, maximum as upper. Whatever the generation that is happening, that should be within the lower and upper operating limits, or minimum and maximum operating limits. Okay, limits or constraints or limitations, all are same. Okay, either you can use all the terms, but operating limits, then limitations, like that also you can use the terms. It is nothing wrong in that. Next thing is that you need to formulate. You need to formulate the Lagrange's function. You need to formulate Lagrange's function. What is the definition for Lagrange's function? Lagrange's function is nothing but, what is the definition? Definition for the Lagrange's function. Lagrange's function is nothing but objective function. Objective function plus some constant into constraints. So objective function, you know, constant. We are choosing this as lambda, then constraints that you need to substitute. Okay. Next, after that, you need to formulate. You need to formulate the Lagrange's function. That is objective function. That is sigma. That is summation I is equal to 1 to n fi of pi plus lambda into pd minus summation I is equal to 1 to n pi. Okay. So generally PD might be greater. So by neglecting the power demand, so by taking that as 0, then what we are doing? We are differentiating. So for the function to be minimum, okay, the for function to be minimum. What we are doing is, so we are minimizing the total fuel cost. No, minimizing all our we are dealing with minimizing. Say for example, I need to find out the maximum cost. In case I need to find out the maximum cost, instead of differentiating, what do you need to do? You need to integrate to certain period of time, to certain limit. Say for example, from the time 1 to 24 hours, or time 0 to 24 hours, or time 0 to 10 hours. Like that, you need to integrate. Okay, integrate. If the function to be maximum, if the function to be minimum, that is minimum, you need to find out the minimum. So then what we are doing is we are differentiating and equating it to 0. So similarly, we are differentiating this and equating it to 0. So after differentiating, this term will become 1. So dfi divided by dpi is equal to lambda. For pi minimum less than or equal to pi less than or equal to pi maximum. If dfi divided by dpi is less than or equal to lambda, for pi is equal to pi maximum. If it is greater than or equal to lambda, then pi is equal to pi minimum. So these are the three conditions.